Vacuum tubes. This is not as relevant to Tesla's technology, but very relevant to medical technology, and explains some of the fascination that people had with studying all kinds of new technologies in the beginning. These days, I think we're a little jaded. Oh gosh, there's research going on. Gee whiz, well, tell me something interesting. But back then, anything, vacuum tubes, Tesla coils, radios, all of that stuff was absolutely fascinating. Had the imagination of the public at all times. And so Jim's going to be able to bring some of that back for us. As a profession, he has a company called Dr. Phineas Volt's Scientific Instruments. He builds replicas of old scientific instruments for institutions, museums, schools, whatever. We also share some work in Oriental Studies. Both of us have done that, and that's kind of interesting. I've never run into people like that normally. So here we are with Jim Hardesty on the lure of the early technologies. Jim?
Thank you, Steve. Or Michael, rather.
I'm not Steve. Never have been.
Sorry. Very happy to be here. I'll see if I can work this mic properly without pumping it up and down. I'd like to thank Steve Ellswick personally for getting all this together and seeing that we all got out here with all of our equipment and so on. That's really great. It does a great job, and I appreciate it a lot. This morning, I'm going to talk about essentially early X-ray work and X-ray and vacuum tubes. I have some slides to show, and I would like to show and talk about the early years of using those vacuum tubes and a lot of the things about them that have considerable curiosity to us all. Things you might not find out about how they were used in the medical profession, and a little bit about the origin of that and so on, to give some clear approach to the earlier ideas and the earlier methods used with vacuum tubes. I'm going to catch my breath and my composure here and decide where we're going to begin looking at the equipment. I suppose that the earliest of men sitting on a hilltop on a winter or summer evening, looking off and seeing the northern lights, the aurora borealis, and marveling over that phenomenon, wondering what that was, and I'm sure postulating a few ideas on what created that glow discharge in the sky. But it really was not until around 1672 that the first actual laboratory production of what we call glow discharge, and I'm referring to excitation and relaxation of gas molecules in a vacuum, giving off visible light vibrations as a result of that excitation relaxation process. So the first thing I'd like to show here is this is not a replica of, but it will display well, I hope, if we can see this. I'll ask if we could have the lights out in here. How dark can we make it? Is anyone down there on the light control? How dark can we do it? Can we Good. What about the back there? Can we kill that? Because you can't see this unless it's real. Beautiful. Looks like we're going to get it. No? One last switch. Here we go. We still have. Marvelous. Give us a moment here for our eyes to get used to the light. Consider that this is an evening in the Paris Observatory around 1675, and a gentleman by the name of Jean Picard is doing some experiments with a Torricelli barometer. That is a barometer that has a lot of mercury available in a long tube, and that mercury is pulling down on the sealed end of that tube and creating a vacuum. But as Picard picks up this barometer and moves it from one side of the laboratory to the other, he notices a very curious phenomenon here that occurred. And if you can watch what I'm doing here, can you see this? Let me put the mic down here. There we go. Can you see this? So all this is in here is mercury that is inside of a glass tube. The vacuum in here is about maybe right now about 1/10 of a torr, and it creates quite a bit of, if you really shake this up, you can see quite a bit of luminescence. Okay. Now, when this was observed, of course, people didn't realize exactly what was happening here. As a matter of fact, Francis Hawksby, who was assistant to Robert Hooke of the Royal Society and a person that built a lot of science demo equipment, made some experiments with this, and his explanation of this, of course, that he called it some kind of mercurial phosphorus, or the phosphorescence created by mercury. However, as experiments went on in later years, we come to realize that this is a phenomenon known as triboluminescence, which simply comes from the Greek word tribo, which means to rub or to create friction. The mercury rubbing against the glass here, simply electrons are rubbed off in the same way as you would rub them off with your shoes as you walk along a carpet, and the electricity passing through the vacuum excites the gas molecules in here, which are, of course, oxygen, nitrogen, and there's some mercury vapor, which gives a little bit of a glow to that as well. So that's what this particular arrangement is. Now, let's move on quickly to the next part of this. We have a vacuum pump here, and I'm going to ask, I can get untangled here.
Plug it in?
Yeah, if we can keep that TV screen down too. We're just going to pump the air. Now, what I need you to do there, Bill, is turn the induction coil on first. This is just a basic induction coil. You'll see the spark generated here. And as we evacuate the air from the tube, we're going to create a situation in which is very much like in the higher atmosphere where the air is more rarefied. And so that's just a basic spark. Now we'll turn this on, and I'm going to ask you to turn it off at a couple of spots as we go along through this so you can see what's going to happen. And you will, there's a switch on the line. It's Friday morning, it's okay. Now, keep a hold of that switch if you will, because we're going to be turning that off from time to time. The first thing we're going to see here is that, provided Murphy's Law isn't working with us this morning, it'll take a few seconds for that pump to evacuate this tube. There it goes. Now, you're seeing the same thing, except in the case, okay, cut the pump for a second here. We'll just watch this. Now, all we're seeing here essentially is the same thing as the spark discharge in the air, with the exception of the fact that, of course, there's a lot less air in the tube. And as a result of that, the spark can travel a lot further because the phenomenon that's taking place here, the electrons that are running across that tube, and you can see as the vacuum is going down that it's easier for the spark to pass across the gap of the coil than it is to pass across the tube itself. So therefore, we turn the pump back on again. Go ahead. We will watch the induction coil will stop, and the discharge will begin to take place again. Now we'll let this go a little bit. Earlier vacuum technologies did not allow for a very good vacuum. You could get a very, very rough vacuum, such as you're seeing here, and this was about as much as people were able to see as the earlier vacuum systems developed. And as time went on, they got about this far. I'm going to turn that off a second. We'll just, and whoops, well, we have to leave it back on. The pump leaks back too much. Okay, go ahead, crank it up again. This is the negative pole over here. You can tell by this particular glow, as well as a little dark space that's forming in here, which was first observed and written about by Michael Faraday, and it was called the Faraday dark space. And we'll talk a little bit about that. I don't want to get too involved with this because of the way that this works. But essentially, we have set up a situation in here where electrons are traveling this way, and free electrons that are already in the gas in the tube are moving along, being attracted toward the positive plate of the tube. Positive ions traveling back this way, collisions taking place in here. There's ionizations and relaxations as well as excitations. Ionizations and recombinations as well as excitation and relaxation of quantum particles in here, creating this particular thing as electrons, which are hit in the orbits of the gas molecules, are pushed to higher energy states. As they fall back to their equilibrium, they give off vibrations that are characterized by the color of the particular discharge that you see. And if this proceeded and continued, and we were able to pump this down far enough, and we had enough electricity, enough potential developed in the induction coil here, we would eventually be able to see a flow of X-rays produced at the positive end of this tube, because the mean free path that the electrons would travel across the tube would be so long that they could gain a tremendous acceleration, work their way down the tube, and smash into the anode end of the tube and produce X-rays by the characteristic methods that X-rays are produced. Whether they would be Bremsstrahlung or characteristic X-rays, it would be both present in their collision of those electrons with other electrons in the orbital structures of the aluminum that the anode is made of. This process continues here, and there are a number of things that will occur as the process takes place, but for the sake of time, I'm not going to spend a lot of time describing that. I wanted to show this because this particular phenomenon that is seen here, the various effects of the discharge in the rarefied air, was something that was beautiful in itself and had a great deal of effect on physicists, natural philosophers in the 19th century, and developed a whole method of study and a whole entire branch of physics which actually changed the entire world and led into 20th century physics with particle accelerators and many of the things that are available today, including the entire vacuum tube technology. This could go on for a while. We're not going to just keep pumping this out because it's going to take a while for that vacuum to get down. Actually, the seal in this is not as good as it could be, so we're not going to get down as far as I thought we might get. Glow discharge, this is called, had been studied through the 19th century, and it led to a number of discoveries that we will now begin to look at with the slides that I have. So, Bill, maybe you could just turn that off, and we will proceed with the slides there. You can see that just returns as the pressure increases inside the tube, and the process reverses itself down to basically a much longer spark inside the tube, and then the coil itself begins to respond by being able to arc across the points that are on the safety gap there, more easily than passing through the tube. And eventually the discharge ceases inside the tube as the vacuum is returning to atmospheric pressure.
Is this connected?
Yeah, that's it. That's good. Now we'll just put the energy to the slide projector and we will proceed. The first slide that we'll see here is just a grouping of the particular phenomena that you see. Okay, there we go. That's not it there. There we go. From some tubes that were pumped out, and this was something from about the 1880s, showing various things. The positive column up top, all these different striations and different dark spaces that are within this glow discharge in here that were observed by Faraday, Geissler, Plicker, and Crookes, and many of the experimenters in this during the 19th century. This was what was really a tremendous thing to view and excited a lot of people. And of course, during the 19th century, the opinion of the nature of light was that it was a wave phenomenon, and that, of course, was from Young's experiments around 1803 of passing light through slits in the cardboard and noticing the wave interference effect. So everyone believed that light, of course, had a wave nature. But this particular amount of studies here began to show, and was proved by Thomson in 1897 to be, in fact, it had a particular nature as well as a wave nature. And also this particular study was one of the things that gave birth to quantum physics, which has so amazingly affected us in the 20th century. Next slide, please. Oops. Yeah, these are a few pictures. What do we got here? Okay, yeah, there we go. These are a few, this was a, yeah, let's have that. Next slide. Okay, there we go. This is an example of, from about the 1840s, a very early vacuum discharge tube that had a vacuum valve on the bottom, and this was to be hooked to actually a static machine, a static generating machine using frictional plates to generate enough high voltage to pass a discharge across this, and the lower end was reached ground by virtue of the vacuum connection. And this was where this phenomenon was first began to be studied. Next slide, please. And these here are some pictures of this particular vacuum tube at work, but I took some pictures of the actual discharge phenomena so that you could see the process as we go down the line. Go ahead, just flip through them. That's getting stronger. Go ahead, just keep going. You can see the Faraday dark space off to the left. And next. And as the discharge proceeds, the light dims down a little bit as the vacuum increases because of the number of gas molecules in there that are able to participate in the actual excitation relaxation process, which gives off most of the light. Next slide. And again, here you can see the Crookes dark space as well as, as well as the Faraday dark space. Now there's two dark spaces, one close to the cathode of the tube, which is to the left hand, and the Faraday dark space is moved out a little bit further into sort of the middle of the tube, and you have these two dark spaces in here. I'm not going to spend time describing this because this is not, it'd take too long to go into that. We'll just look at the phenomenon and move on. Next slide. And that's, again, next slide. Shows even a really very, very large dark space there. Next slide. And here is, as you saw in the earlier list of the phenomenon from the 19th century, this shows the positive column, these various striations across here, essentially produced by the fact as the electrons travel down the tube, when they experience collisions with and recombinations with positive ions in the tube, as well as new collisions with other gas molecules, the electrons of other gas molecules. As the speed of these electrons increases and decreases, it breaks up the process, whether or not they will be an ionizing collision or an exciting collision. The exciting collisions produce more light, and the ionizing collisions and recombinations produce less light. So this is why these striations are in here, because the speed of those electrons traveling along there is reduced and increased. In the 1850s, Geissler, a German glassblower as well as an experimenter, and working as an assistant and instrument maker for Julius Plücker, who was one of the first people to really work with vacuum discharge from a natural philosophical standpoint and so on, designed a bunch of tubes of this nature. These were called Geissler tubes, and their basic process was to show how beautiful a discharge running through a vacuum tube could be. He used several types of different glass in here, and this was the rage in the 1850s. Even along from there, there were many public shows done using these tubes because it was something enjoyable to see. If you, next slide, I think I have a, yes, you can see what it looks like, what is running in. There's some different colors because there's lead glass and there's some soda glass. I believe there's some uranium glass in there. And if you see down at the right-hand end of the tube, you can see that that's the negative electrode because of that purplish glow in the dark spaces in there, which is basically the engine of this process. You can always tell the polarity there. Next slide. This is another type, another, particular winding of the glass and all that to make it beautiful. Next slide. Yeah, and there's that operation running. You can see that in this particular case, the negative end is at the left side of the tube because of the dark space and the glow that is there. Next. This is another type. Go ahead and move along. Next slide. You can see that operating. This is, again, different types of glass construction and types of glass to show the colors that would occur from the electrons striking the glass walls of the tube and creating different phosphorescent effects. Next slide, please. Next slide. In the 1860s and into the 1870s, a lot of work was done with the phenomenon known as cathode rays. Now, Plicker himself had noticed that there was some kind of an emanation coming from the cathode, or in this case, the right-hand electrode in the tube. But his vacuum systems were not high enough to be able to observe this very well. It had to wait until Crookes made major improvements to the Templer vacuum system, or the mercury lift kind of pump, where they would let mercury fall down a tube and pull a vacuum in the system. Crookes improved upon, actually, I guess the major name to remember there was the Sprengel vacuum pump. Crookes improved it a great deal and was able to get a much higher vacuum. And this tube here in Germany you call this the Hittorf tube, but if you were in the West, in England or in America, you called it Crookes tube, because this was a design that Crookes made. And the observation that he made in this was that this emanation coming from the cathode could actually, he noticed it fluoresced on the glass walls of the tube, but he also noticed that if he put an obstacle in the way of this, that obstacle would cast a shadow on the glass walls of the tube. And began, Crookes himself and some other people, thinking about the fact that this may be some kind of a particle emanation as opposed to a light wave. However, you could easily see that both, as a matter of fact, from looking at this, it seems that this is a light wave casting a shadow on the wall of the tube. So there began a great controversy over the wave and particle nature of light, which raged on until the end of the 19th century with, I suppose, Thomson's discoveries, but perhaps even more so Einstein's photoelectric work in the 20th century and so on, to really put that to rest solidly. Next slide, please. This is an example of a tube of that nature. This tube, I believe, dates from about the 1890s. It belongs to the Antique Wireless Association back in New York State. You can see that the iron cross in the center of the tube there, if you can see it clearly, it's kind of warped or wilted. And the reason why is because someone ran this tube a little bit too long, and the impact of the electrons on that metal caused it to heat up to the point where it actually melted over, so the tube doesn't function anymore. However, it does take marvelous X-ray pictures, and this particular tube is made of German glass, and it's something you really can't get anymore, and so there's a marvelous, beautiful apple green glow that the front part of this tube exhibits when it is working. And to see this working is fascinating. It has fascinated me since I was about 14 years old and began dealing with this experiments and so on. And it always is a good topic of jokes around our dinner table and so on, because my wife often chides me about my desire to collect antique tubes of this nature, and X-ray tubes and so on. And every time I run into a friend or an acquaintance somewhere who has the same addiction as I do, she always laughs and says, how is it possible that, you know, I say, well, some people collect cars and some people collect coins, and then there's some of us that collect these vacuum tubes because they're fun to hold, and I mean, not only their historical value, but they work. And to see the many phenomena that physicists in the 19th century observed and that led to such great discoveries is a kind of a participation in that, which in fact really, it's very cathartic, and so that's why we do it, I guess. Next slide. Yeah, there's another view of the tube with a better picture of the collapsed Maltese cross that's in there. Now, you notice that the anode of this tube is down in the base neck of the tube down there. It isn't anywhere near the cathode, and and the rays that emanate from this tube go straight down the tube and strike the glass. And as we looked at this discharge tube over here, we saw that the attraction of the discharge went from one electrode to the other. But in fact, because of the way that the positive ion conduction field is set up inside the tube, the anode literally is brought to within centimeters of the actual location of the cathode. So it doesn't matter where you put the anode, especially as the vacuum increases. The electrons that are produced by secondary emission of ions striking the cathode of the tube, as well as electrons accelerated in the field that are present in there as free electrons are accelerated in the field coming out, and also directly they propagate in 90 degrees to the cathode. So regardless of where the anode is, this tube will work. As a matter of fact, all you need is one electrode in there to make it work, especially if you're using high frequency currents. Next slide, please. This was a design of tube made by Crookes in the early 1870s, in which because of the propagation of the cathode rays, and we can't use the term electrons yet because we haven't discovered them, but this propagation of these cathode rays came out from the concave cathode, and it was noticed that if you made it concave, you could focus where the particular, where the electrons could be focused on a target someplace, which was another fact that led to the understanding of cathode rays as actually electrons, subatomic particles involved in this, crashing into this screen in here and causing it to light up and glow from the heat from that impact. At any rate, and they didn't know it at the time, but they were producing X-rays when this was done. And that there was no way of observing that at the time, but they had already been having this phenomenon occurring. So this is your earliest X-ray tube. Next, please. This gentleman is Wilhelm Conrad Röntgen. Röntgen was a fabulous German physicist, and he was at the University of Würzburg in 1895. And being a meticulous experimenter, absolutely meticulous. He was so meticulous that, having taken the work of Hertz and Lenard before him, and they had said to him, well, Professor Röntgen, look at this phenomenon of getting electrons actually to pass through a small aluminum wall in the front of one of these type of Crookes tubes, and observing the process that was taking place. We won't go into that now, but he actually, through his absolutely meticulous work and the way he had everything set up, he actually was holding up some lead weights in front of this tube that he was working with, and it was and he'd already seen a piece of screen glowing off in the distance, and he had noticed that there was a very curious focus phenomenon of the wires from his induction coil cast a shadow on that screen. And he felt that perhaps there was some kind of a spark emanations coming from the interrupter on his induction coil, or something that was casting that light on there. And then he realized that perhaps this was actually these cathode ray emanations coming out of the tube that people had seen before that caused fluorescent screens to light up. But what really got the man was when he picked up a lead fishing weight between his thumb and forefinger, and wanted to move and noticed that the lead, of course, resisted the passage of these rays. But when he put his fingers actually in there as well, he noticed that the shadow of the bones of his hand were cast upon the screen, which was quite a start for him, I'm sure. Next slide. And this is one of the first pictures that he actually took of a colleague by the name of von Kolliker. Albrecht von Kolliker was a physicist at the university with him, a very early X-ray picture. You can see that it certainly does not possess the sharp contrast of pictures today, and we'll explain a little bit about that in a minute. Next slide, please. And this was, there's a controversy about this, whether Röntgen was using a Crookes tube or whether he was using this type of a tube, which, if you notice, it says Hittorf-Rohre, which means a Hittorf tube. And it's a little different from the Crookes design of the pear-shaped tube that people say he used to discover X-rays, for that was the kind of tube that was being used by Hertz and by Lenard before him. But it does say here in German, it says Hittorf-Rohr mit der Röntgen seiner Strahlen entdeckte, which means this is the tube with which Röntgen used to discover his rays. And so whichever tube it was, of course, you can see the obvious effect here is that electrons, or in this case cathode rays, we haven't discovered the electron yet, being emitted from the negative electrode, striking this plate, which is in the middle of the tube, would give off X radiations as a result of the process of electrons striking other electrons in the orbitals of the aluminum metal or tungsten. Probably that was aluminum in that case. Next slide. This is an actual very early version of this kind of tube for experimentation with X-rays and cathode rays. I'm not sure that actually this is a tube that was used to produce X-rays, because it doesn't have the proper electrodes in it to do it, but it certainly would give certain effects coming from the glass, because a lot of these tubes, X-rays were produced actually off the glass wall of the tube by the cathode rays or electrons striking the glass wall of the tube and producing characteristic X-rays from the actually atoms involved in the glass. Next, please. This is a little bit further development here, where they finally, in the maybe about 1896 or 1897, knowing the process involved in producing X-rays, yet Röntgen himself in 1895, if you read his paper called On a New Kind of Ray, you realize that although he can describe to you what he did and he can describe to you the results of his experiments, he cannot tell you what is happening. He cannot explain to you why this is occurring, and that cannot happen until J.J. Thomson's work and so on, and early into the 20th century. But to produce X-rays, this was the first kind of a, shall we say, a professional tube, or a tube that was being manufactured for experimental work. Next slide, please. This was an experiment done in 1897, and what it shows here, you can see in the background the outline of the vacuum tube, and you can see to the left hand is a little bit of a concave cathode, and on top you see what is the anode of the tube. And but you can see what they have done is that they have driven a bunch of nails into a board that's put on top of a photographic paper. The point is that you can see where the X radiation is emanating from, and it is the wall right in the front of the tube there, so that the cathode rays stream down the tube, and by crashing into the glass wall of the tube give off X-rays. And this was the early understanding of how you would design a tube. Next. Here again this is a picture from a dentist by the name of William Morton from Boston, and an early induction coil in the background there that was used, laboratory induction coil, taking an X-ray photograph of one's hand, and you can see that it's basically the same type of tube that is a little bit earlier phenomenon. 3 electrodes in that Röntgen type tube we looked at with a plate in the middle. The X-rays come down, you have the tube on an angle, the X-rays come down, and then you can take the photograph. Very primitive from Morton's laboratory, probably about 1896. Next. Here's another example of a tube we showed earlier, the same kind of thing. You can see that actually in doctors' offices and so on, when it came time to take pictures of broken bones and so on, it really must have been quite an experience for people. I'm sure that if you will, the placebo effect of all of this equipment, not to mention the hair being raised up off your arms and so on by the amount of electricity passing through here, must, I'm sure, have given many quick cures, better than the actual treatment that the doctor may have given. You know, if it didn't scare the person half to death, I don't know. But you can imagine, you know, what you would have here. Next slide, please. This is a slide that is in here backwards. It happens occasionally. This is the Frost brothers, Gilman and Richard, from Dartmouth College, supposedly reproducing the first or the early X-ray experiments in 1896. When the announcement was made, everybody had to run out and try to get their equipment together and see what they could do. The person has a broken arm and they're taking a photograph. The actual lighting in the tube that you see there is actually impressed upon the picture in another method, because you wouldn't show that. That was done for the pure effect of being able to see. If you had that much light, you would never be able to see the discharge in the tube, so they did that, but not really what it would look like. 1896 at Dartmouth College. Next slide, please. Are we there? Okay, and here is another example of the same sort of thing. Some poor devil's foot there with a 100,000 volt induction coil, and actually in the background there's some curious equipment. I haven't had time to really go over that, but it does have a sort of, it smacks of some kind of high frequency work in there. That's quite possible. Pear-shaped tube, as you can see. Next slide. This particular tube, touching on the high frequency equipment that Tesla was using at the time and the availability of smaller high frequency power supplies and the experiments, like I say, that were going on at the time. This was a tube that was developed to use high frequency electricity. It had a double-sided anode in the tube. You could get X-rays coming out of both sides of it using a high frequency coil, and it worked quite well. Next slide, please. What's going on here? Okay. There is another very early X-ray tubes sort of put together in a well-cobbed fixture there, and running a small experiment with some kind of film and penetration experiment with some kind of metal brads or something running down there, so when you would take the X-rays down onto the film plate, you could see what kind of focus problems were going on, because they had a lot of problems with this in terms of inverse currents producing X-rays both on the positive, on one side, and then you would have some inverse current involved in using an induction coil, so you would get X-rays being produced off the cathode of the tube, and they would interfere with the focus of things. So there was some problems with that. So they ran a lot of experiments like this to try to understand why they were getting foggy and not well-defined X-ray pictures. In some cases they would, in other cases they wouldn't, because of the characteristic of the actual induction coil power supply and how great the inverse current being produced in that was that it would generate X-rays. A properly built one with a proper capacitor and proper brake mechanisms would not give that difficulty, but that was not known very well at the time about how that worked. Next slide, please. This is Thomas Edison and his assistant Clarence Dally. This is a rather great slide because Dally was the first person to actually die from dermatitis from overexposure to X-rays. I think actually this photograph shows why. He was given to, was very easy to put your hand in front of a tube and to take the pictures that, or take a look at things and focus your tube and so on. And so that's Edison in the front, obviously, with a fluoroscope, which was his invention, a calcium tungstate screen that was inside of a box with an eyepiece so that you could have total darkness in there and observe and be able to look at whatever you wanted to X-ray with that. That was an Edison invention. To his left hand, by the way, is a Sprengel vacuum pump. That is a big pool of mercury up top and a fall tube where the mercury drips down and draws a vacuum, much in the same way as Piccard's barometer did in the 1670s. And down the bottom there's a pitcher that catches the mercury, and somebody simply pinches the tube and then reaches up and pours the mercury back in the top, and the process continues. Very laborious process. It takes quite a bit of time to do it. Next slide, please. This is Clarence Dally in Edison's laboratory. He's dealing with light bulbs here, but Dally was an expert glassblower and made a great deal of X-ray tubes early on in the period of X-ray, starting in 1895. And of course, when you made X-ray tubes and you pumped the vacuum down in them, how would you test one out? How would you know when the vacuum was right and things were working right? Well, it was really easy to do. You simply hooked the tube up to a high voltage induction coil, took your fluoroscope in one hand and put your other hand between the tube and the fluoroscope and see exactly how good an X-ray picture it would take. But as you can see, he did quite a bit of work in this, and after a few years he actually, his contribution to X-ray science was great. Unfortunately, it was his life. And he was the first martyr to X-rays in the United States. In fact, I think in the world, nobody, he was the first to get a really heavy case of dermatitis for obvious reasons. Next slide, please.
It's not taking this slide. Yeah,
it's Murphy Day here. Maybe. What do we got here? There we go. This is Edison's exhibit at the, it was in New York City, and there's an X-ray. You can see the gentleman standing with the derby there looking in a fluoroscope. They had an X-ray, a tube inside of a box set up in there, and people would come along, and at this exposition they would go in and actually take it. You see the fellow's hand is in front of you. You can take a look at your own hand in there. If you take a look at the far right hand in the back, that's Clarence Dally back there regulating the induction coil, passing the high voltage to the tube. This was a very common thing to see, that in all the big department stores at this time there were many displays about X-ray. They really wanted to introduce it to people and tell people what a marvelous discovery that it was and how many amazing things could be done with it. So it was very common to go into a department store and be able to get X-rayed, but the poor people that actually ran the display ran into quite a few problems after the number of years for obvious reasons. Actually, you could go into a shoe store into the early 1950s and have your feet X-rayed, if any of you remember that, until they finally made that illegal as well, and it has its danger. Not so much to the people putting their feet in there, but the guy that runs it every day, especially as unprotected as those units were, produce considerable amount of problems. Next slide, please. Again, this is this is your doctor's office, and I don't know, I feel nervous enough when I go to the doctor's today when everything is nice and spiffy and clean and official and
all sorts of scientific. I imagine people went in there these days, and here you have a few sawhorses and the induction coils in the back of the doctor. He's got a pen in which he's drawing what he's looking at inside on the outside of the gentleman's chest that you can see there. And of course the doctor himself has his himself well placed there, so that not only is his face getting bombarded in his eyes, but if you notice some other valuable parts are getting treated with x-rays as well, which was obviously a problem. And this is the 1897, 1898, something like that, when this was about just setting up a rough x-ray laboratory to use in a doctor's office. Next slide, please. Here again is the same office with a view of the big induction coil in the background. And I love those induction coils. What a beautiful thing they are. And down on the base there, the tube is in a box, and it looks like they've improved on the stretcher mount that they have there, but nonetheless, and there's a little filter between the box at the base where the tube is and the patient himself. Is a little copper aluminum filter they had there to try to filter out some of the x-rays produced by the inverse current of the induction coil that would cause a double focus and blur the picture. That was one of the ways they tried to deal with that. Next slide, please. And here's our doctor again getting a good treatment of x-rays himself. You can imagine doing this day after day after day. The effect of the amount of x-rays that you yourself would be exposed to would be considerable, and by the dermatitis began to be a real problem, usually with both hands and the face, where was the major difficulty that occurred. And so they put lead glass into the fluoroscopes. It still meant that your hands and parts of your face and so on would still be exposed to x-rays considerably, not to mention the Compton scatter effects that would take place from these x-rays. So it goes on. Next slide, please. It's just another laboratory. Next slide, please. Oops.
Come on.
Yes, fun. Oh, there we go. Now the process, this is a very interesting process, looking at this particular tube here. When early x-ray tubes were made, they were just simply made and pumped out, and they were used without having any kind of regulation in there. And one of the problems that occurred is that the vacuum constantly was being increased when you discharge electricity through the tube by basically driving molecules of the gas in the tube into the walls of the tube, as well as through the process of the discharge, the ionization and processes, the actual gas in the tube would become more and more rarefied over use, and the tube would become harder and harder, as they call it. That is, harder and harder to place a discharge across the tube. So you take more and more voltage, and the penetrating power of the x-rays would increase, and the doctor trying to take the x-ray or the fluoroscopic examination of trying to look at somebody's leg, and after a minute or two of using the tube, you couldn't see the bone anymore because the penetration power of the x-rays is so great. So they had to come up with a process of being able to reduce the gas pressure, or rather to increase the gas pressure in the tube, and that was first done by putting a little bit of asbestos or something in the part P up there, and if the tube got so hard that the discharge couldn't pass between the anode and the cathode, a spark would jump from B to P and reduce and cause the asbestos in there to outgas. That would lower the vacuum in the tube, and the tube would begin to operate a little bit better. So they went on from there. How are we doing on time, Michael?
Just about there.
Okay. Well, I've done it again. Got halfway through this. Go ahead. Let's just flip through quickly. There's another tube here. Go ahead. I'll just show you a couple of... not again. These are some, just flip through quickly here. These are some of the tubes that they use, that kind of a regulator. There we go. Oops. There's a tube, you can see that had to be drawn in because they couldn't get a good shot of it. Go ahead, just flip through them, Bill, quickly, and we'll finish up here. This is the famous Myron Kasabian in his laboratory in Philadelphia. This is, to the right-hand side, is a Tupler-Holtz static machine, which is powering the X-ray tube in the front here. Kasabian was famous. It was also a martyr to X-rays, but he was a famous name in early X-ray work and so on. Next. This is another X-ray unit here for Let's see the tube out at the edge, and this might be a high frequency piece of equipment, I'm not sure. Next slide. Just flip right through them. Oh, there's another tube that's a part of that.
I think it's time for another projector.
Well, I do believe that it isn't Michael or oh, okay. There's a
Random selection.
yeah. Go ahead. Keep that's the tube was.
It just isn't taking.
This is a tube in a mount that has a lead front to the thing that allows the tube to protect you from the X-rays coming from the tube. See the regulator on top. Go ahead. See if you can get any more. Well, I think that it isn't the time or Michael's whatever. I think it's Murphy's Law that has caused me to, okay, here, let's look at this one quickly. This is a water-cooled tube, by the way, with a much more refined regulator on top. We'll talk about this regulator in a second. The regulator was connected to the positive and the negative side of the tube, but the wire that runs down from the top of the regulator to the cathode end of the tube, you would regulate that for how far a discharge you would want to get across the tube, and then you would simply you would know how hard the tube would want to get by the distance the spark would travel across there. And then there's a piece of mica up top between the two arms that go into the regulator vessel on top, a little piece of mica in there. And as long as you could see the mica glowing red, and you would know that it was outgassing, and then you could, and it would introduce gas into the tube and lower the vacuum and make it run better. Also on the other end, there was water was pumped through that, and that vessel allows water to run all the way up in the back, so it hits against the target in the anode of the tube and cools it down for long therapeutic uses. This was called a pylon tube. Go ahead, flip through quickly if we can get anywhere. There's the target of the tube. You can see where the impact of the electrons on there has actually burned a hole in the target. And there's a little focus element in there. Go ahead. Keep going. That's another view of the tube and another view of the same tube. Go ahead. I just wanted to keep going to maybe we can get to the couple of really amazing shots. Just keep flipping because we're out of time here. That's a tube in operation. That photograph was taken in 1908. Keep going. We'll get to a better shot here. We can show you something. Yes, this is actually a gas X-ray tube in operation, and you can see the ion impact cloud down by the cathode. You can also see the cathode stream focus traveling down and striking the target of the tube. And if you look down at the bottom, you will notice that that tube was built out of lead glass, but at the bottom there is a window of German glass, and down there the X-rays are allowed to pass through the German glass, and the effect of the cathode rays, actually, which are in there, and the electrons bouncing around striking that German glass, produces that apple green glow down there that I talked about earlier. Flip it just to see if we can, yeah, see there, the current is now inverse, so that the anode is now negative and the cathode positive, and you have that ion impact cloud around there that you can see again. And here is actually, you can see the beam striking the target in the tube and causing a phosphorescence to occur where the electrons are impacting on the tube. You can see some of them are actually impacting on the copper part of the tube, resulting in some sputtering occurring, and that's why a lot of times old vacuum tubes like that are copper plated on the inside because of that particular thing, and then they break down because the copper conducts. It's another picture of the same thing again. This is that high frequency X-ray tube in operation. You can see that beautiful apple green glow that occurs when they're working properly. It's done with German glass. Go ahead, keep going. That's the same thing as before. There's a nice 1890s Templar static machine used for X-ray experiments. That would have been in a doctor's office to take photographs used. Isn't that amazing? It's a beautiful piece of equipment. That's it in its operation there. Large induction coil. Well, I think that I've taken up my time and have done there's a beautiful induction coil as it stands itself with the interrupter. And there's that slide for you, Bill. That's a marvelous piece of equipment. I've used up my time and been less than professional here because I have not been able to finish in the allotted time, so I will stop here. And this is called, by the way, the unipolar X-ray tube. We talk about monopolar X-ray tubes in Tesla's work. This is called a unipolar X-ray tube, which was used. You could actually run a high-frequency power supply in the base of that, press that against various parts of the skin and make X-ray photographs right at the local area that you wanted to make just by, using that. And it's quite a curious tube. I'm sorry that oh, there we go. There's the Murphy's Law again, so stop there. That's good. That's where we'll pick up for the next side of things. Thank you very much. I would be happy to show some of these slides perhaps at a later time and talk a little bit more about this. I try my best, but time seems to be the demise of my work. Can never confine this to a short enough period of time. I thank you very much, and I'll be happy to answer questions. Perhaps we can look at these a little more later. Thank you.